Welcome to the Deep Dive. Today, we're digging into something really exciting in the LLM space efficiency.
That's right. We're looking at the BitNet b1.58 2b4t technical report from Microsoft Research.
And the headline here is pretty staggering. A 2 billion parameter model that performs like its full precision cousins, but uses way less memory, energy, and is faster.
Exactly. It achieves this through native 1-bit training. It's potentially a huge leap, especially for actually using these powerful models in the real world.
Yeah, this isn't just tweaking things. It could really change how we deploy AI. So for all you AI researchers and engineers listening, especially if you're battling with those massive model resource demands,
this deep dive is definitely for you. We're going to unpack how they pulled this off, the architecture, the training, everything.
and what it actually means for the field.
Yeah.
Because honestly, the computational cost of these big open source models, it's becoming a real barrier.
Oh, absolutely. A huge roadblock, makes them impractical for so many things, like running on your phone or, real-time applications.
So this paper, BitNet b1.58 2b4t, positions itself as a solution. And it's the first open source native 1-bit LLM at this kind of scale, right? 2 billion parameters, trained on, 4 trillion tokens?
Yep, 4 trillion. And that native part is key. Our goal today is to really figure out how they got this efficiency without losing the performance we expect.
Okay, let's jump in. The paper kicks off addressing that core challenge, the sheer cost of running these big models. Memory, compute, it adds up fast.
It really does. Full precision weights just demand so much.
And that's where 1-bit LLMs come into the picture. The basic idea is extreme quantization. Yeah.
Exactly. You're drastically reducing the number of bits used for the weights, sometimes activations too, down to like binary or ternary values.
Like compressing an image, but for the model's parameters. Fewer bits, smaller size.
Precisely. Fewer bits means less memory, obviously, but also potentially much faster math using bitwise operations. That should mean less energy and faster inference. Theoretically, anyway.
Now, you highlighted that native aspect of BitNet b1.58. Why is that distinction so important for us?
It's crucial. Most previous attempts either quantized after training a big model.
Post-training quantization.
Right, and that often hurts performance quite a bit. Or they built native 1-bit models, but they were much, much smaller.
Okay, so they couldn't really compete with the big guys.
Exactly. What's exciting here is that BitNet seems to avoid that big performance hit by training with this low bit setup right from the start. And they did it at a pretty significant scale, 2 billion parameters.
So the promise is performance like the big models, but without the crippling resource needs. That leads us to the architecture. They swapped standard linear layers for these custom bit linear layers.
That's the heart of it, yeah. The bit linear layer is where the efficiency really comes from, but without sacrificing the model's capabilities, it changes how weights and activations are handled.
How so? Let's start with the weights.
Okay, so weight quantization. During the forward pass, the weights get crunched down to just 1.58 bits. They use this Absmein scheme.
Absmein. Absolutely.
Yeah, absolute mean quantization. It maps weights to just 3 values. -1, 0, or +1.
Oh, okay. From like 16 or 32 bits down to just 3 possible states. That's a massive reduction.
It's huge. That ternary representation is where 1.58-bit comes from. It allows for incredible compression and potentially super efficient math.
Okay, so that's the weights. What about the activations?
Activations get quantized too, but not quite as extremely. They go down to 8-bit integers using an Absmein strategy absolute maximum, and this happens per token.
Right, so weights are super compressed. Activations keep a bit more detail. Seems like a smart trade-off. The paper also mentions Sublayer Normalization. What's that doing?
Sublayer normalization, or sublin, it's there mostly for training stability.
Oh, okay.
Especially with this kind of extreme quantization, you need to keep the gradients under control, stop them from exploding or vanishing. Sublin helps with that.
Gotcha. And they made other interesting choices too, right? Like using squared ReLU instead of SWIGO for the activation function.
Yeah, ReLU squared, or ReLU2. They cite some other work suggesting it helps with model sparsity and just works better computationally in these 1-bit networks. It seems like a deliberate choice for this kind of architecture.
Makes sense. And they're using RoPE, Rotary Position Embeddings.
Yep, standard stuff now for handling positional info in transformers.
But they removed all the bias terms from linear and normalization layers. Why do that?
Well, it cuts down the parameter count even further, adding to the efficiency. Plus, it can apparently simplify the whole quantization process.
Interesting. And finally, the tokenizer is LMA3s.
Correct. Which is great for the community.
Yeah, familiarity helps adoption.
Definitely. It's a solid bi-level BPE tokenizer, handles text and code well, and lots of tools already support it. Makes it easier for people to actually try BitNet out.
Okay, so a fundamentally different architecture. Now, how did they train this beast? They mentioned 3 phases: pre-training, SFT, and DPO.
Right. Pre-training first, then supervised fine-tuning, and finally direct preference optimization. No RLHF, though they mentioned that as future work.
Let's start with pre-training. They had a 2-stage learning rate schedule. That sounds unusual.
It is a bit different. Stage 1. Start with a pretty high peak learning rate, then a standard cosine decay.
Why so high?
Apparently, these 1-bit models are just more stable during training than full precision ones, so you can be more aggressive initially.
Oh, okay.
Then, about halfway through, they suddenly drop the learning rate way down and do another cosine schedule, but much lower, like a cooldown.
A cooldown phase. What's the point of that?
The idea is to let the model refine what it learned, maybe focusing on higher quality data during that second, slower phase.
And they did something similar with weight decay too.
Yep, mirrored the learning rate strategy. Stage 1, cosine schedule for weight decay up to 0.1, probably to prevent overfitting when the learning rate is high.
Right.
Stage 2, turn weight decay off completely, set it to 0, let the model really settle into a good optimum with a lower learning rate.
Clever. And the data, what were they feeding it during pre-training?
A mix. Lots of public web text and code things like DCLM, FineWeb EDU, but also some synthetic math data to boost reasoning.
And they used a 2-stage data strategy too.
Yeah, aligning with the learning schedule. Stage 1 was more general web data. Stage 2, the cooldown, focused on more curated, likely higher quality data sets.
Okay, pre-training done. Then comes supervised fine-tuning, SFT. What data did they use there?
A bunch of diverse instruction following and chat data sets. Things like WildChat, LMSYS Chat1M, WizardLM, Slimorca, public stuff mostly.
To teach it to follow instructions and chat properly.
Exactly. And they also added more synthetic data, GLAN, and math scale, specifically to improve reasoning and handling complex instructions.
And they used a specific chat template for the conversational parts.
Standard practice, yeah.
Yeah.
Just a clear format for system prompts, user input, assistant replies. Helps the model learn the structure of a conversation.
Any optimization tricks during SFT that stood out?
One thing was how they handled the loss calculation. Instead of averaging the loss across tokens in a batch,
Which is pretty standard.
right, they summed it instead. They found summing actually led to better convergence and performance for this model.
Interesting.
Also, it seems the 1-bit model liked a relatively higher learning rate during SFT and needed to train for longer, more epochs, compared to typical full precision fine-tuning.
Okay, that makes sense, perhaps needing more time to adjust with the quantized setup. And the final phase,
Yeah.
DPO, direct preference optimization. Why use DPO instead of, say, RLHF?
DPO is generally seen as more efficient and stable than full RLHF. You don't need to train a whole separate reward model. You optimize the main model directly using preference data pairs of good versus bad responses.
Streamlines the alignment process.
Exactly. Less complex, less likely to become unstable during training.
What preference data did they use for DPO?
They used ultrafeedback and MagPi. Both contain lots of human judgments on AI outputs, which helps steer the model towards being more helpful and safe.
And the DPO training wasn't too long.
No, just 2 epochs reported. They used a low learning rate, a specific DPO beta value, and leveraged optimized kernels from the Liger library for speed.
And the result? Did it mess up the model's core abilities?
Apparently not. They noted qualitatively that it aligned the model effectively without significant degradation elsewhere. That's a good sign.
Okay, so that's the architecture and the pretty complex training process. The big question, how did it actually perform? They threw a lot of benchmarks at it.
Oh yeah, a really broad suite. Language understanding and reasoning tests like ARC, HelloSwag, MMLU, World Knowledge with Truthful QA, reading comprehension.
Trivia QA, Bull Q.
Right. Math and code using GSM-8K, Math, Human Evil plus Thero. And then instruction following and chat with IFEVL and MTBench. A very thorough evaluation.
And they compared it against similar-sized full precision models, right? LAM-A31B, GEMMA1B, Q1.58B.
Yes. Importantly, they used instruction-tuned versions of those models and reran all evaluations with a public pipeline for fairness.
Smart. So what did Table 1 show? The efficiency metrics must have been striking.
Absolutely striking. The non-embedding memory footprint for BitNet was just 0.4 gigabase.
0.4 gigabit compared to what for the others?
Several gigabytes typically, so a massive difference. Energy use during decoding was estimated to be way lower too, and CPU latency using their framework was also significantly down.
Okay, that's the efficiency win. Huge. But performance, did it keep up?
Remarkably, yes. Looking at the task scores, BitNet b1.58 was highly competitive. It actually got the best results on several benchmarks: reasoning, knowledge, math.
Better than the full precision models.
On some, yes. On others, it was very, very close to the top full precision models, maybe slightly behind on a few specific tasks, but the overall picture is strong performance across the board. Near parity, basically.
So near performance parity with a tiny fraction of the resource cost. That is really compelling.
It really is. It suggests the trade-off is heavily in favor of efficiency here.
They also compared it to post-training quantized models, like Qwen 1.5b quantized down to INT4.
Yes, Table 2 covers that. And while INT4 Quantization definitely helps Qwen save memory,
BitNet saved even more.
BitNet used even less memory, yes. And crucially, BitNet generally performed better than those INT4 models.
So native 1-bit training seems better than post-training quantization, at least in this comparison.
That's what the results suggest. A better efficiency performance balance by training low bit from the ground up.
And the final comparison was against other 1-bit models, some native, some quantized later.
Right, Table 3 looks at that. And BitNet b1.58 2b4t came out clearly on top.
Better than smaller native 1-bit models and bigger models quantized down to 1-bit.
Significantly better overall performance than all the others they compared against, yeah. It really highlights how effective their native training approach seems to be, especially at this 2 billion parameter scale.
Okay, impressive results, but how practical is it to run this thing? Inference with 1.58-bit weights and 8-bit activation sounds tricky. Let's talk GPU inference first.
Yeah, standard GPU libraries aren't really built for this kind of W1.58A8 setup.
W1.58A8, right, 1.58 bit weights, 8-bit activation.
So they had to develop custom CUDA kernels specifically for that kind of matrix multiplication.
And they use that pack, store, load, unpack compute trick for the weights. How does that work again?
Okay, so you can't efficiently store just -1, 0, or +1 directly on the GPU memory, usually. So they pack 4 of these ternary weight values into a single standard 8-bit integer.
Okay. 4 weights squished into 1 byte for storage in the main GPU memory, the HBM.
Exactly. Then, when the kernel needs them for computation, it loads that packed byte into the faster on-chip SRAM.
Unpacks it back into the 4 separate -1, 0, +1 values.
And then does the math with the 8-bit activations. The goal is all about minimizing how much data you have to move from the slower HBM, which is often the bottleneck.
Clever. But it sounds like even with custom kernels, current GPUs aren't ideal.
No, they mentioned that. Current hardware isn't really optimized for these ultra-low-bit operations. Future hardware designed specifically for this could unlock way more speed and efficiency.
Makes sense. What about CPU inference? For those without fancy GPUs.
They covered that too. They developed an open-sourced BitNet.cpp.
BitNet.cpp.
Yeah, a C++ library. It's a reference implementation for running 1-bit LLMs, like this one on standard CPUs. It has optimized kernels tailored for CPUs and this specific quantization scheme.
So you can actually run this model, which performs pretty well, directly on a regular CPU.
Apparently so. Fast and accurate inference directly on the CPU. That's huge for accessibility.
Yeah, it really opens up deployment possibilities.
Oh.
Okay, wrapping up this deep dive. BitNet b1.58 2b4t feels like a genuinely big step for efficient LLMs.
I think so too. It really shows that native 1-bit training can work at scale, delivering performance close to full precision models, but with drastically lower computational needs.
The implications for deployment, especially in places with limited resources, are pretty profound.
Absolutely. And the open sourcing of the weights and the inference code, both the CUDA kernels and BitNet.cpp, is fantastic for the community.
Gives everyone a foundation to build on.
Exactly. And they lay out clear future directions too. Scaling up, hardware co-design, longer sequences, multilingual, multimodal, lots to explore.
So the final thought for our listeners, especially the researchers and engineers tuning in, think about what this level of efficiency means for your work. If resource constraints were suddenly much, much lower, what could you build?
How does this change the game for AI on edge devices or even in massive distributed systems? What new doors does this open?
Definitely a lot to chew on. Thanks for joining us on this deep dive.